Kia ora e te whānau, ko Jason Ingham aho. My name is Jason Ingham, and as head of the Department of Civil and Environmental Engineering, it is my great pleasure to welcome you all here tonight. As you know, we are here to honour and remember the career of Mick Pender, and we're looking forward to that immensely. Ko te mihi tuatahi ki te runga rawa, te timatanga o ngā mea katoa. The first acknowledgement is to the very highest, who is the start of everything. Ko te mihi tuarua ki te whare e tā wharotia nei tātou. The second acknowledgement is to this house that shelters us here. Ko te mihi tuatoru ki te whenua e tākatoa nei. The third acknowledgement is to the land that is lying here. Ko te mihi tuawha ki irakua wehe ki te pō. Moi mai, moi mai, moi mai rā. The fourth acknowledgement is to those that have departed. May they rest in peace. Tēnā koutou, tēnā koutou, tēnā koutou katoa. So I'd like to start tonight with some brief housekeeping before we get into the main business. First of all, just a reminder to please turn your phones off. Should you need to know, perhaps not right now while you're in this room, but afterwards, the bathrooms. We happen to have a map here, and so from where you are, you can sort of follow that red arrow and make out that men's and ladies' bathrooms are by room 1401. The evacuation protocol is that if we have such a thing as an earthquake or similar, we quietly make our way out onto Simon Street. That's where we will assemble. There is an iPad outside, and we would ask for you to check in, and this is not necessarily to do with the ticketing that you sort of received in your original messaging, but instead is part of our COVID protocol. So if you haven't already checked in through the iPad, could you please do so at some point before you depart tonight, so that we have that for COVID reasons. And just in case you didn't sort of notice, there is nibbles and bubbles afterwards, and we would very much invite you to stay, linger, mingle and talk rather than sort of rush off, though we do appreciate some of you may have other things to do. So, as you're aware, we have assembled here tonight to celebrate the career of Professor Michael Pender, who most of us refer to as Mick. But before we do that, first of all, we actually have a gift for Mick's wife, Jan, and we would like to thank her for the many years of support that she has provided Mick throughout her career. So, Jan, I'm pleased to say here, I have a little gift for you. Many of us that assembled here tonight have known Mick for many, many years in one form or another. For myself, I've first met Mick in 1986, which is now 35 years ago. Oh my gosh. Since then, Mick has been my lecturer and my boss, my colleague, my travel companion, and we have stood side by side through at least one major natural disaster, so I suspect we will hear some of that tonight. And when I sort of think for myself personally about the role that Mick has played in my career, I can't help but think that I was really very fortunate to have such an exemplary role model that I could pattern my own career after. So I just really wanted to make that personal comment, and I think Mick will have had a similar influence over many of the careers of many of the people in this room. Mick, the floor is yours.
Thank you, Jason. Well, thank you all for coming. Jason and I had a telephone conversation this morning, and our topic of our conversation was the flowers that Jan has there. And we had both separately come to the conclusion that we needed to do that at the beginning of the session. Jason had one reason. I wanted to acknowledge Jan's wonderful support of me over coming up to 51 years. There's a common phrase out there, behind every successful man is a woman. That's a load of rubbish. It's not behind, it's beside, and that's where Jan has been. Always supporting what needed to be done, where we needed to go, including in 1977, abandoning her beloved Wellington. I also had another reason for wanting to do this at the beginning of the session, because about 2 years ago, Engineering New Zealand promoted me to being a distinguished fellow. And I had to make a speech there, and I finished by saying how much support I'd had from my colleagues, and spoke about them in a very thankful way. And somehow, in the excitement of getting everything finished, I did not mention Jan. So I don't want to be in the same position this evening, getting to the end and getting a bit sort of excited about what was happening and what had to be said, and then forgetting about dear Jan. So now I can start. I've got. Thank you. Does it work?
Try again. Forward.
Can we go backwards? Can we get...
Oh, this is the first slide.
Pardon?
This is the first slide, I think.
There we are. So along the path of putting this together, I realised that there were many people who had contributed to what I had been doing over the years, and I needed to acknowledge. And in thinking about this, there were some of them that I realised I may not have actually acknowledged in the past. So I'm taking up a bit of time with stories of interaction with other people. And what I'm going to present is not in chronological order. It sort of goes back and forth a bit, hopefully not making it difficult to follow. I grew up in Christchurch, attended St Bede's College and then University of Canterbury. My first year was 1962 on the city site to do engineering intermediate, and then out to Ireland with the fine arts students in 1963 to 1965, completing the BE. I come from a large family. Each of my parents were one of 8. And the effect of that was that I had 80-something cousins. I was in about the middle. And of that horde, I was the first one to go to university. Both sides of the family were people with a practical turn of mind. My father would say, "Put the book down. The time for reading is after dark. There's work to be done." My earliest intentions at primary school were to take up tool and die making, that being the high end of machine shop work. I learnt something of this by reading books from the Canterbury Public Library about lathes and machine shop work. I was too young to borrow books from that part of the Canterbury Public Library, so my cousin, my older cousin Joe Harrison, would borrow them for me. He was a school teacher and had been impressed that I had made an aquarium for his classroom. Then about the time of starting secondary school, I realised that I should go to university. My ambition had been to design aircraft. And the first book I ever had on mechanics before I went to secondary school was a Christmas present I had requested, The Mechanics of Flight by A.C. Kermode. Now, can I get it back? So I had the copy of the first edition. I have no idea where that went to, but this is what I found recently, and you can see it was a very popular book. I don't know how many editions came after 10, but 10 is a pretty good record. In the final year at secondary school, two of us, David Selby, who some of you know, along with me, were included in a day-long bus trip organised by the Ministry of Works for final year Christchurch students who might study engineering at university. We were taken to Otamatata, the site of the construction of the Benmore Earth Dam on the Waitaki River. There we were addressed by the project engineer, Jack Ridley, a former Rhodes Scholar and Member of Parliament who was a most impressive speaker. We were also taken to the dam site to observe the construction of the earth-filled dam and explained to us the function of the compacted clay core and the gravel shoulders. Before we got back to Christchurch that evening, I had settled on civil engineering. However, the interest in aircraft is still there, and I haven't had another jump in what I wanted to work on since. So it's been a long association in civil engineering. I had a good all-round career at St Bede's in Christchurch and was head day boy prefect in the final year, and two teachers had an important effect on where things were heading for me. Father Leo Evett, who taught maths in the 3 school certificate years, so 9, 10 and 11, managed to extract and organise to good effect my modest mathematical abilities. And Father Kevin O'Connor taught chemistry in the school certificate year, year 11, and the bursary year, year 13. In the school certificate year, he explained just before lunch break one day where the atomic weight came from. Up went my hand and pointed out that his explanation would give a whole number for the atomic weight, but these were not whole numbers, so he was delighted with that. and was a very effective chemistry teacher in the upper sixth form. Well, let's jump ahead a bit to my appointment to the University of Auckland. The appointment process was done via telephone conversations with the head of department, Peter Taylor, who I knew. He had been one of my PhD examiners, and we had contact through the New Zealand Society for Soil Mechanics and Foundation Engineering. Appointment was a very simple process with direct involvement with the head of department. I did have some good referees, as this was after my postdoctoral period in the UK. A few days later, after accepting the offer, another letter came from the University of Auckland. And I'm wondering what this is, and I open up. Dear Dr. Pender, with regard to position whatever, we regret to advise you the position has been filled. So an unnecessary letter for me. An immediate phone call to Peter Taylor. And despite what Peter Taylor said to the HR people, I discovered later that he could be rather volcanic. They clearly did not put the letter aside. As about 10 years ago, Leanne Wotherspoon, soon after accepting a position in our department, received a Dear Dr. Wotherspoon, we regret to advise this position has been filled. So a special letter, kept perhaps to test the fortitude of certain people. So for me, things turned out well and ended up with me in just the right place. An academic position is an immense privilege. particularly if it eventually leads one to understand the importance of teaching. Working with Peter Taylor taught me much. His clarity as a teacher, his good grasp of the fundamentals, his ingenuity at developing mechanical apparatus for cyclic testing of soil. He often said that to be a successful geotechnical laboratory testing work, one had to be something of a mechanical engineer and a civil engineer. And I guess, Alan, today you would say an electrical and electronic engineer as well. And his hand on the practicalities of real engineering was very important. So let's have a look at Peter Taylor. So there we are. So he was head of department starting 1977, so just about the time I was appointed. So let's go backwards a little bit again now to the PhD study. So this started in 1966, and Harry Hopkins, the head of the Civil Engineering Department at the University of Canterbury, when I told him I was thinking of enrolling for a Master of Engineering, he suggested to me that maybe I should think about doing a PhD. And looking back on it, perhaps the best advice I have ever received. When I had finished the PhD and asked him to be a referee for my application for a University Grants Committee postdoctoral fellowship, he was quite sure that I would receive one. And he was correct. I did not realise that as those were early days of PhD study in New Zealand, anyone who successfully completed a PhD in New Zealand was entitled to a postdoctoral fellowship. And I've got here brackets, modest money from the New Zealand University Grants Committee. So there's a picture of Professor Hopkins. And thinking back to the early stages of my PhD study, I can only feel sorry about today's generation of PhD students. I spent my beginning graduate 6 months in the library. So this was the first half of 1966, checking the literature, the main geotechnical periodicals, the Australia-New Zealand conferences, and the international conferences in soil mechanics and foundation engineering. With one exception, the 1965 conference proceedings, which occurred in Montreal, but were not yet in the university library. But I knew that Laurie Wesley, whom I had not met at that stage, had attended, and I wrote to him asking if I could borrow the proceedings. A week or so later, a neatly wrapped parcel arrived with the volumes. At the end of that period, I had a good appreciation of the range of the geotechnical literature. I discovered that it was also fortunate to have English as my native language. I had come across an English abstract of a paper written in French. According to this abstract, the paper had the answers to every question I had. I had the French-English Geotechnical Dictionary from the library and a girlfriend studying French. Off we went. Fortunately, it was a shortish paper, because when our English version was in front of us, it bore no semblance of what the English abstract had promised. Lesson from this exercise: if the paper's not written in English, too bad. My PhD work was independent Good enough to get the degree, but perhaps no great achievements, but got me to the right place with good skills about soil laboratory testing, design of soil mechanics laboratory equipment, and the basics of the Cambridge critical state soil mechanics ideas. Another graduate student, George Mullinger, had also developed an interest in this critical state soil mechanics, so we used to have conversations in the corridors trying to sort out various bits of the complexity of all this, and that was a fun time. My supervisor, Tom Dodd, had good mechanical skills and was helpful when I was building equipment and was a strong supporter of my work. Tom appeared in the lab one afternoon with a new book that had just arrived in the library, Critical State Soil Mechanics by Schofield and Roth, published in 1968, which he knew would interest me. It answered with great clarity a fundamental question that had been bothering me for some time, and so developed my appreciation of the ideas of critical state soil mechanics. So I've got a picture of the book here, and what did that do for me? Well, the bottom of page 47, the top of page 48, the bit I've marked there had the explanation I was after, and that paragraph explains the goings-on in equation 627 and 628. And it was all so simple and so clear that one couldn't help falling in love with the clarity of it. And you'll notice I did quite a bit of marking on that page. But let me confess to being a fairly enthusiastic book marker. But what do I use? Only ever a pencil. A pen, no, and those coloured marker things, oh, what could be wrong with a person to do that? And the next one is a picture of my supervisor, Tom Dodd. And looking back, and this is where putting this story together has been quite engaging, with thinking about contributions that other people had made, and one in particular that I think at the time it never occurred to me to acknowledge. Dr. David Elms, then a senior lecturer, but long since a full professor, he assisted me with my experimental work. He taught me how to apply foil strain gauges as I was making my own pressure transducers, so needed specially stable strain gauges. He also proofread parts of my thesis where I was writing about the principles of work hardening plasticity. Fairly exotic theoretical ideas for the 60s, and he came back with encouraging comments. David was not my supervisor, but on thinking back, as I said earlier, I only now have realised he was good enough to keep an encouraging eye on what I was up to. So here we are. Here's a picture of now Professor David Elms, but that's him in about the 60s when he had arrived only a few years earlier at Canterbury teaching our class. From now, I will go to finishing the PhD and working with Ministry of Works and Development, Central Labs in Lower Hutt. I was in charge of the Geotechnical laboratory and had the amazing riches of 5 technicians, Never since have I enjoyed anything like that. Some of the material we tested, so we were doing laboratory testing for the parts of the Wellington urban motorway and some of the building foundations around the city. We did further testing on this material on my return after a postdoctoral work, and the material we were testing was derived from Wellington greywacke. Now, greywacke is the basement rock of New Zealand, which unweathered is a very hard material. But with sufficient time and a warm, moist climate, is converted to stiff, sandy soil. So time there perhaps is not going to be a couple of days, but anyway, so there are parts of the soil, the profile, where the soil appears, and it occurred to me that it had been explained to me that it's called a residual soil, and so I wrote a paper on this testing work for the 1971 Australia-New Zealand Conference on Geomechanics, and this became my first conference paper. Conference took place in Melbourne, and fortunately for me there was someone there from Hong Kong who was knowledgeable about residual soils, and he made comments supporting my main points. And then in 1980 the Australia-New Zealand Conference took place in Wellington, and I presented another paper in which more of the test information had been gathered together and processed. Some of that test information which was organised by Ian Parton during his time at Ministry of Works Central Labs. And the conclusion from this work was that the friction angle was quite a reliable parameter, but the cohesion was rather more difficult to deal with. So on the left-hand side there, we've got the friction angles, and you can see the variation is relatively small, although there's a strong relation between the how closely the soil particles are packed together, here described by void ratio, could also have been given by density, but for the same range of materials, the cohesion parameter, the sort of average value was somewhere in here at about 50, and then the upper bound is up here, and the lower bound would be negative. So that confirmed many people's suspicions about the unreliability of the cohesion parameter. Central Labs was a good environment for work such as that published in Melbourne and Wellington. John Galloway, in charge of the lab, had worked in dam design and introduced me to the idea of residual soil. And John Robinson, in overall charge of the laboratory and computer services, was also a supporter of our work. So about 1973, I think it was, Jan and I departed for Cambridge to do a postdoctoral assignment. My entree to Cambridge was via an Australian academic, Dick Parry, a fellow of Pembroke College in Cambridge, whom I met on my first conference in Auckland in 1967. By then I had ambitions to go to Cambridge, so was very pleased to meet him. So here he is on leave from Cambridge at the Waterways Experiment Station in the US. Jan was a brilliant success at Cambridge. She got on so well with members of the soil mechanics group and their families. She was even taken to college dinners, where college members We're allowed to bring women guests, but not their wives. And she also got on very well with the local Cambridgeshire people. A very different crowd to the university people. So we came away from Cambridge with a broad perspective on the inhabitants of Cambridge and the surrounding countryside. The 18 months we spent in Cambridge were idyllic. Easy to get from Cambridge to London, and also Cambridge was a good stepping off point for travelling in our second-hand Mini, which cost us £140, to other parts of the UK. More importantly though, the soil mechanics group at Cambridge had a wonderful tradition of hospitality and made sure that all visitors of the group were made to feel welcome. The Pender model is what I did as a postdoctoral scholar and what my PhD had prepared me for exactly. I added a little piece to the Cambridge clay model, so making modelling a big region of soil behaviour more realistic than the assumption of simple linear elastic behaviour. Geotechnical, a very high-profile journal, Dr. John Hawley helped me edit my draft paper. He worked with the DSIR Soil Bureau in Taita in Lower Hutt and had received a PhD from Cambridge about the time I finished mine at Canterbury. Geotechnical fluctuates in position 1 and 2 at the top of the Geotechnical journal. So it's quite an achievement to get between their covers, particularly as their acceptance rate is well below 50%. So they have a rather staid-looking cover. You can see it's got sort of French overtones there because originally when the International Society was set up, it was a combined effort from the English and French. So this little bit here, well, that symbol in the middle of the cover goes back to the writings of Coulomb. And then, more importantly, the title page of the paper. In the first volume, in volume 28, number 1, 1978. And on the left-hand side, the abstract in English, and on the right-hand side, the abstract in French. I can't now remember where I got the abstract in French from, but anyway. And so what was the paper about? Well, a nice thing about this model for soil behaviour, you can look at a page of equations, many of which are off-putting, but it can also be displayed in diagrammatically or graphically in a way that looks rather easier to understand. So these are a couple of diagrams that I drew. So there are 3 axes we're worried about, 2 stress axes and the void ratio, which represents the packing together of the soil particles. And there's a line that comes down the middle called the critical state line, where all the test paths are supposed to finish up sitting nicely on that line. And you see there's a sort of curved paths here, and that generates a surface over here in which all the state paths for soft clay would sit. Stuff that at the soft end a potter might use. And then as you decrease the water content, it gets stiffer. And what I did was that all this region under here is a much bigger area of soil behaviour and is quite important, and certainly to the materials I had come across at that stage and come across since, is stiffer. And so over here, the Cambridge people, for want of something better to do, said, well, let's just assume the stress paths are vertical and everything along here is elastic. So what that would mean over here is that if we started off on this one here, we would have a vertical path that goes up to there and then moves across. On this side, goes up to here and moves across. And the curvature of these paths here is what I managed to put into the model and caused them much more excitement than I had anticipated. And so I was dealing with so-called over-consolidated soils, and I didn't quite pick it up at the time, but looking back on it, it occurred to me they were just so excited that someone would turn up, knew something about their model, and was able to just sort of put another couple of little notches in it. The other thing that's interesting to talk about is the question of citations. Now, people working in the scientific area on a topic, if they find some information about what it is they're working on, will note that and reference that paper in what they're going to write afterwards. And what intrigues me, these are two papers of mine. The top one up here is the so-called Pender model, and then this one down here is another paper I wrote about the same time, looking at deformation of ground around the construction of a tunnel, and just pointing out that using some slightly different boundary conditions gave more satisfactory results. So the top one was published in 1978, the next one was published in 1980, and yet there's a steady stream of citations that seems to continue on and on. And this one up here, that's about, in 2014, it got 8 citations. Down here, we're about 4 and 3 citations. But the fact that it's still picking up a bit of notice, I like to kid myself, that must mean there's something important about these papers, that they're still and so the total number of citations between 1978 and this far in 2021 is only 125, the other paper 77, but yet steadily there's a sort of click, click, click of someone, for some reason or other, referring to it. The other important contributor in Cambridge was Peter Roth. Professor Peter Roth. He was the leader of the soil mechanics group at that time. Amazingly hospitality received from him, and very interested in the work that I was involved in, and very encouraging in what I was doing. So I've always been grateful for what he did. And so let's take a little break from the technical stuff and talk about a few other people who were very helpful in my career as well. The next one is someone else who was a graduate of his PhD from Cambridge, but he was Professor of Engineering Science here in the Engineering Science Department in the faculty. And I also benefited from working with him. His theoretical abilities were way beyond mine, but I provided some explanation of soil behaviour and background as to what type of behaviour would be accepted. So there are several papers with both our names on them, and also some of them with students. And they've also received good citations. So I've been very lucky to be associated with Ian Collins. Next person that I need to acknowledge is Nigel Priestley, the late Professor Nigel Priestley, because he's a graduate from the University of Canterbury, and he and an Italian structural engineer established the graduate earthquake engineering program at University of Pavia, and eventually he got me involved in that as a visiting professor. So that was a wonderful adventure for both myself and for Jan. Another important person was Dr. Jeff Martin, a graduate of Auckland, and he resigned from our civil engineering department and went to work in consulting engineering in the US. And so the position I filled in 1977 was the one that he had vacated. And he was very helpful to me, and I had a brief leave in 1980 and worked at the University of British Columbia on cyclic testing of sand, and he did the work that got that into place. Our former Dean, Michael Davis, came to the faculty from a geotechnical background and was a supporter of our activities and has kept in touch with our work and extended presentations and attended presentations we've given in London in recent years. And finally, somewhere in the room, there's Lucas Hogan. Now, Lucas is a PhD graduate in the department, and with Liam and myself providing suggestions, established a very successful geotechnical field testing site at Silverdale for lateral load testing of steel tube piles and for the rocking of shallow foundations. So the picture of Lucas is here, and we've got a pile of steel kentledge that's being bolted together and eventually gets craned onto the top of this rig, and then the whole thing lifted onto the site with a very large crane. And that was only my second experience of working on a site with those, but every time I'm utterly amazed at the precision with which the crane operator, 10 millimetres, or 20 millimetres, right, and they just seem to know exactly what to do. So again, very grateful for all those people who've contributed to my activities. Well, being a university staff member, after having come back from this postdoctoral fellowship, it occurred to me an obvious thing to do was to apply the so-called Pender model to soil test data on Auckland residual clay. So 2 PhD students, Zacchaeus and Drawen and Vaughan Meyer, did good laboratory work and showed that Auckland residual clay did not know about critical state soil mechanics. And in brackets here I've got, Peter Taylor had warned me that it would not work. And why did it not work? Well, so in this diagram here, I've got plotted a large collection of test data. Down the middle you can see some open circles, and if you look at those you can imagine yourself putting a curved line through those. Well then all the little crosses there, if the soil was behaving itself, should lie very close to that imaginary curved line. And you can see it's the worst of measles type plots. So clearly, as I say, Auckland residual clay didn't know about critical state soil mechanics. And then going a bit further, we did some CT scanning. We have somewhere in the university a small a device that can do CT scans on small things. They were thinking that probably people dealing with arthritis in rats would be very interested in CT scanning, and they were a bit surprised at the number of people who came knocking on the door and said, well, can we do some CT scanning? So it's the same technology as the medical people use, except it's just a smaller piece of equipment. So here we've got a small specimen of soil, diameter about 20 millimetres, height about 20 millimetres, and at the beginning with a low confining pressure you can see there's a very complex void structure here, and there are some quite large voids that we called macro voids, and then if you gradually increase the confining pressure, in this case we went as far as 800, and you can see you get rid of most of this. So in other words, you close up all these macro voids and you get a more uniform void structure. Well, for the critical state soil mechanics to work, you would need a uniform distribution of voids rather than that rather messy plot. The next one I'd like to go on to is the PhD research that Ken Mills did. So he was one of my fairly early PhD students, and the Energy Research and Development Committee agreed to fund his PhD, and he was going to work on the Western mine at Huntly, looking at the stiffness properties of the coal and particularly how much movement takes place when a chunk of material is removed. So Ken and I, we got a bit fed up with getting in our car here and driving to Huntly, getting togged out and going down onto the mine and out again and driving back to Auckland. We kind of felt that what's it take? How long does it take to get to Huntly? About an hour and something. But one particular day, we had what must have been the most successful afternoon's interaction, because we got in the car here, moaned about driving to Huntly, and then started saying, well, what are the problems we've got? We've tried to be measuring the in situ stress in the coal. We can't get anything to stick into place properly. And so we started toing and froing and backing and forth with ideas. And by the time we got to Huntly, we had worked it out. And what's more, the conversation was so intense and back and forth that I could never remember afterwards whose idea was which, etc. And Ken agrees the same. So a very, very successful afternoon's driving. And here's the device, the so-called ANSI cell, Australia, New Zealand. Well, it used to have an S in there. Australia, New Zealand stress inclusion, and somehow or other the S is gone, and so Australia, New Zealand is still there. Now this is a later version, and its diameter is about 58 millimetres, whereas what we developed after our car drive was something that had a diameter of about 38 millimetres. And the problem was putting an inclusion and gluing it into the coal, and then coming along and overcoring, and pretty well anything you put in the coal would just break. So our solution was, first of all, we needed the strain gauges. So these are rosette strain gauges, 6 of them, so a total of 18 separate strain gauges. They needed to be right at the surface and stuck to the coal. And then we needed a very flexible membrane. So this is polyurethane here. and that's easy enough to make. And thirdly, we needed to have some pressurising system that would glue it to the surface of the coal. So you drill the hole in the coal, clean it, and then there's kind of a recess in this part here, and you fill that with epoxy, then push this thing into the hole, get it all positioned where you want it to be, then apply some air pressure and inflate the membrane against the coal. And you hold that pressure overnight so that the membrane becomes bonded to the coal. And then our next breakthrough was to realise, well, we've got the thing stuck in there. We have an ability to apply air pressure. So basically, we've got a type of pressure meter. So the next stage was to increase the pressure in there and measure the strains in the coal. Now, that would tell you how many of the strain gauges are working satisfactorily. And secondly, those that are working satisfactorily, you can work out the stiffness of the coal. So that was sort of 3 quite big step forwards there, all achieved in a couple of hours one afternoon. And this is a developed version of the cell, which Ken went on to develop considerably. So the process, first of all, we've got access and we drill a hole in the rock. In our case, it's coal. Then we come along and drill another hole, smaller hole in the middle. So drilling this hole here alters the stresses in the coal in that region. Then drilling that hole further alters the stresses in this region here. And the final stage, here's where the cell has been inserted. The final stage is the so-called overcoring operation. So we come in here and drill this bit out and release the strains in that part there. So there's mechanically, it's quite a tricky operation. And Ken Mills tells me they now do it routinely down to 800 or 900 metres. So the device is a long way from where you are. But that works. But then there's quite a lot of complicated mathematics to figure out what the strain release during the overcoring means in relation to the in situ stress in the coal up here. So not a simple operation. Now here's, Ken sent me examples of one that worked very well at a depth of 850 metres, and all 18 strain gauges there are performing the way they should. So that's a very nice looking result. Here's Ken Mills, taken fairly recently. So you can see it's not an office suit and tie job. And what he's doing there is painting a special epoxy onto the membrane. Then that gets inserted into the in a small hole and left pressurised overnight for the epoxy to set. Then, as I say, we have to unscramble what the measured strains are. So Dr. Mary Farmer has been helping us with that, and Mary Farmer is well known in the engineering science department here. So where's that leave me? Well, the next little bit there is just to take another side trip and talk about the question of patents. So when we had developed this thing and it was working successfully at Huntly, Uni Services took out a patent with my name and Ken's name as the inventors. and they held that patent for a few years. And then when Ken moved to Australia and joined Strata Control Technology, they took over the patent and have done much more development. About the same time, a structural engineering colleague, Ian Buckle, came into my office, and he had been and still is working on energy dissipation devices for protecting structures against earthquakes. And he said, "You're always talking about the capacity of soil to absorb energy. Why don't we try clay?" And I said, "Well, no, Ian, that's not going to work. Clay won't dissipate enough." But I countered with, what about dense sand of small, hard-grained particles? And looking back on it, I think that's where we made a big mistake, because the device was a spectacular way of crushing sand together, and we should have gone along to the mineral processing people with a serious suggestion of here's the technique you need for crushing minerals. Next stage is Professor Meyer, who had assisted us with funding from the Energy Research and Development Committee, but also he took the initiative of suggesting that I be appointed to a professorial position. I had referees Professor Peter Roth, who by that time was Professor of Engineering Science at Oxford, Professor Ted Brown, who was a Professor of Rock Mechanics in Brisbane, and what I didn't know, Professor Colin Brown at the University of Washington in Seattle, where I had presented a seminar in 1980 and then impressed him with my informal corridor teaching during a visit he had made to Auckland. So ever since, extremely grateful for Ray taking that initiative. On the teaching front, Peter Jackson said, "If you want to learn a subject, you need to teach it." And Peter was a member of a mechanical engineering department. And I'm very proud of my development of a final year undergraduate course in foundation engineering. Took a couple of decades here, but just adding a little bit year by year by year. And I'm fairly sure I've developed a much more useful textbook than any of what must be the collection of the most boring textbooks on the face of the globe. Somehow or other, foundation engineering hasn't picked up something that's good to pick up and read. So I reckon I've made a contribution there. And what makes me so sure of that? Well, it was the response I got from students. And the theme that went on and on and on is, thank you for the examples, etc. And that we had a few students who would come each year from semesters in various parts of Europe, and they would say that this teaching was better than anything they had in Europe. So, very contenting. But one thing they didn't complain about was the value for gravitational acceleration. Now, if you walk into any engineering class and say, what's the value of the gravitational acceleration, they will all spout out 9.81 metres per second squared. And I just say no. The value we're going to use is 10. And then go through with them the percentage difference between the 9.81 and the 10, and it's a bit less than 2%. And 2% when you're dealing with properties of natural materials is not anything to worry about. So where did I get the successful use of examples? Well, I had written a paper for the earthquake engineering community in the early 90s about pile foundations, and I got quite a bit of good feedback there about the worked examples. So I eventually got the message that the way the engineering mind works is not looking at a page of equations, but looking at some worked examples. But thinking back even further, this style of lecture room presentation might have come from the teaching of Dr. Mary Harding, teaching mathematics and engineering mathematics at the University of Canterbury in 1962 and 63. Typical lecture, she would come in and give you a bit of theory, then write an example on the board, put her sheet down and just stand there and out of her head work out the example. And doing that over 2 years, there was only one occasion where she needed to go back and have another look at her crib sheet. So I think I can give a certain amount of credit for that as well. And the thing that I found very satisfactory on reflecting, Jan is telling me that the time is flying. It's all right, Jan. I'm looking at these people out there. This is what I mean by being by my side. Last year's exam for foundation engineering was all via computers, etc. And so the final examination was open book, open everything. And so there was no way of invigilating the exams. So I set an exam that was rather more based on sort of office, design office questions. And that seemed to go down quite well with the students. And I realised that was probably the most realistic examination I'd ever set, because it was kind of putting the students in a design office environment. They had all the information they wanted. They had a lot of information, actually, and they just had to know how to find their way through it. Some stories about the university. Well, the most interesting one is the acting deanship role, to cover the gap between the departure of Roy Sharp as dean and the arrival of Peter Brothers as the next dean. Somehow or other, we agreed that the role of deanship would be split between the 5 heads of department. So there's myself, Peter Jackson, John Boyes, John Shen and David Ryan. And we split up various tasks. I somehow ended up with the grand title of acting dean that you've got at the moment, Gerard. And the interesting thing about this time at the university, there were a lot of changes taking place, and the university introduced a formal budgeting system. So every faculty had to put on the table how much money they needed to run their operation and be prepared to justify it. Well, this sort of activity had never gone on in the past, and so we all learnt a great deal. Not only what we had to do, but what some other people were trying to do. Nevertheless, we were all relieved when Peter Brothers arrived. I often wondered if we pack too much material into our engineering degrees. I think the answer has to be yes, as the students are not given enough time for mulling over what they've learned so far. There's always something else coming, or a test next week, or another project. When I was first on Senate, Colin Maiden, the Vice-Chancellor, so this would have been 1985, Colin Maiden, the Vice-Chancellor, would say that at 12,500 students, we were just the right size for the university. But then the government funding model switched to bum on seats, and the country was trying to get participation rates up to similar numbers in the OECD. Trade qualifications became devalued, and a degree was supposed to be what everyone needed. We now, of course, know that this has not worked. We've got wonderful facilities at Newmarket, and at one stage there was a sort of thread of conversation in the faculty that maybe all of engineering should be at Newmarket. But then the new building next door arrived, so that's not going to happen. And during this period, civil engineering has now returned to being the largest department in the faculty, and Jason has done so much to establish the reputation of our department to a very high position on the international ratings. Pumice sand has occupied a lot of our time. Laurie Wesley first suggested that pumice sand would be worth doing some serious research on, as it looked like it was a material that wouldn't tell one about whether a material was dense or loose. So basically you didn't get an answer out of pumice sand. So a great deal of work has been done on pumice sand, a large number of graduate students. I have been asked by David Hopkins, then president of the New Zealand Society for Earthquake Engineering, to lead a reconnaissance following the Edgecombe earthquake in March 1987. Reflecting on this a year or so after the Darfield earthquake, I was thinking, well, how much liquefaction would occur in the Rangitaiki Plains with a similar magnitude earthquake to the amount of liquefaction that occurred on the Canterbury Plains, to think nothing of what happened regarding liquefaction in 2011. So quite a bit of research has been done on that as well, led by Rowley and a number of PhD students and people working from Canterbury. And it seems that sand or soil with sand containing pumice particles in it is not quite as susceptible to liquefaction. The other thing that I have talked about a lot and was only going to mention in passing here was to do with rocking foundations, something that Jason got me onto following from a conversation he had with Peter Smith, a consulting engineer in Wellington. Tom Algie was the initial student working on this project, but others, Ravi Salamath, Luke Story, Jeremy Toe, and Armin Kamazala and Marlon de Guzman have contributed to the effort. Tom designed this rig shown on the side there, with some weighting on the top lent to us from Pacific Steel, and you can see it's a rather miserable wintry day with plenty of water around the place, and this is Tom here who's using a hydraulic jack to just pull this rig in this direction here, and then we let it go and get the so-called shake-back response. And what happens is there's a very interesting shape of curve that develops in the initial pullback. So before we do it, and simple mathematical expression to describe that, and from that we've been able to work out how one might be able to design rocking foundations to resist earthquake loading. What happened to Tom? I've lost Tom. Ah, well, sorry boy, sorry. And from there, we realised that the standard bearing strength information given in the literature, once you have vertical load, horizontal shear and a moment, it's much more interesting just a shallow foundation with vertical load on it. And taking the rather horrible looking expression for the bearing strength of a foundation with 3 actions, it's surprisingly simple to work out this bounding surface here. And I've spent quite a bit of time working on that. I rather liked it to the shell of an armadillo, although in fact it's just the top half of something, it's the same below. But a French colleague said, "No, Mick, no, not an armadillo, it's a rugby ball." And underlying all this, you all will have seen this, walking down the beach at low tide on that nice firm band of sand, and you'll notice that every time you put your foot down, there's a change takes place in the sand, and the ground surface rises slightly, and you get a sort of a drying out there, and you can see it leaves an impression afterwards. Well, that's a very interesting, quite difficult character of the way sand behaves, and it's been something that we've been battling with for years, trying to figure out constitutive models for it, way beyond the Cam Clay model, but it's only now that there are decent models for that, and so here's one that's implemented in the finite element program that's available from Open Seas, and that includes that place. And not only do you get beautiful pictures, we could almost take the lettering away from that and hang it on the wall, couldn't we? So we've got a vertical retaining wall sitting in here. On the top one here, we've got the lateral displacement contours, then we've got the settlement contours, then we've got the volumetric strain contours, and notice there's a band operating up through here, and the shear strain contours, and there's a band operating up through there as well. Well, these blue incline zones here are telling us where the soil behind the wall is going to fail. So it draws a pretty picture. It's very tedious finite element modelling to get there, and Armin Kamizada has spent several years of his PhD time getting that system to work. But it really all just goes back to the shallow foundation pictures we were showing before. They're a rather more sophisticated version. Well, there's Armin and Jeremy Toe, another of the students who worked on this, and somehow I'm sorry I've lost Tom. Now, I'm not quite finished, I'm sorry to say, Jen. but one of the other things involved in is some consulting work. Not a large amount, but in terms of keeping the academic engineer's feet on the ground and being aware of what consulting engineering people have to deal with day by day, the consulting work is very helpful. So the sort of things I've been involved in, well, we talked about in situ rock stress measurement at the Rangipo Underground Powerhouse, Energy Research and Development Committee, deformation of coal seam in an underground mine, how to get something of the terminology that the geotechnical group use to be similar to what the structural engineers use, so hopefully we can get a more cooperative community, and most of that was based on earlier work of Peter Taylor. Earthquake resistant design of rocking foundations. One example we looked at was a digester at a paper mill, so a very tall, narrow, tubular structure that seemed to come through the Edgecombe earthquake very satisfactory. But the other paper making equipment were destroyed, and you can guess what I said. It's rocking foundation effect. We've also been involved with the Wairaki and Tauhara consent for continuing the geothermal operation there. So a lot of very deep drilling done and laboratory testing of the rock cores and sorting out what those properties might be. The foundations for the Oaki cooling tower was a good example of a very tall structure where you didn't need to use pile foundations. In fact, it was much more satisfactory not to use piles. I'd had a few trips to Dunedin to look at the squeezing of one of the dams at Waipuri number 3. Pile driving conditions at Cashin Key and helping sort through an arbitration between Port of Lyttelton and the contractor. Some work on geotechnical aspects of the Britomart project. Cyclic lateral displacement of the Cycle Point Wharf in early years after construction. Systematic evaluation of transportable moisture limit for shipping cargo of iron ore, which Rowley was involved in as well. And the last interesting thing was there was a hotel, a rather old hotel that was going to be refurbished in central Auckland a few years ago, and the people doing the refurbishing got a bit too enthusiastic about what they did to the foundation and the building collapsed. So you can see there's quite a range of things there to be involved in and does help one's teaching immensely. Well, a closing comment. One can achieve much in a working lifetime if you don't fritter away the evenings watching TV. So, my thanks to the university for paying my salary for all these years, the facilities, the library access to journals, which I still enjoy, and finance for travel to overseas conferences, collaborators, colleagues and the departmental staff, students, and of course family. And I guess I said when we had a function a few weeks ago that really in my time with the university, civil engineering has been a very happy and cohesive department, and that's something we're all very grateful for. So thank you all for your patience. Thank you.
Kia ora koutou, I'm Gerard Rowe, I'm the Acting Dean of the Faculty of Engineering, and it's my privilege to make some closing remarks tonight. Mick, thank you for sharing your thoughts on research, on teaching, on professional work and the university's HR procedures. Thank you for over 50 years of exemplary service to the profession, to the faculty, to your colleagues, and most importantly to your students. Mick has been recognised by the profession on many occasions. He's a Distinguished Fellow of Engineering New Zealand. He's a life member of the New Zealand Geotechnical Society, a life member of the New Zealand Society for Earthquake Engineering. He's been the recipient of many awards. He received the Fulton Downer Gold Medal in 1985 and then again in 2011. He received the Supreme Technical Award for Engineering Achievers in the area of building, construction and amenities in 2005. He received the Turner Award for Professional Commitment in 2006, the Rayburn Award in 1978 and again in 1998, and the Structural Award in 1986 and 1993. Within the university, in 2005, he received a University of Auckland Sustained Excellence in Teaching Award. Mick, the esteem with which you are held is underscored by the huge attendance we see here tonight, and also by the very many requests we've received from people who can't be here for a copy of a recording of the lecture you've just delivered. Your work has made a truly lasting impact, one that has changed students, the faculty, and the discipline for the better in many ways. Personally, I've always appreciated your wise counsel, your pragmatism, and how you were readily available to lend an ear and to help solve any problem. We're going to miss you very much. We wish you all the best in retirement, and thank you for everything you have done here.
Thank you all. Good. Okay. Thank you.
I'll bring the proceedings to a close, and I'll invite you all to head outside to enjoy some refreshments and networking.